we will solve to any equation which is non-exact, first find out integrating factor by these three rules. First is, if my minus nx upon n is function of x alone, then fx, then there is the integrating factor e raised to integral fx dx. Second, if nx plus my upon m is a function of y alone, that is say fy, then e raised to integral fy dy is the integrating factor. Third, if mx plus ny is not 0 and m and n both are of homogeneous function of same degree, then integrating factor is 1 upon x into m plus y into n, and this is the integrating factor. Solved. So now Mr. Rajesh will solve some of the example using integrating factors.
So first is y dx plus 2x minus y e raised to y dy equal to 0, and second is x square y dx minus x cube plus y cube dy equal to 0. So these both are in the form m dx plus n dy equal to 0 form. So first we consider the first example, y dx plus 2x minus y e raised to y dy equal to 0. Now if you check the exactness of this differential equation, you will get that my is not equal to nx, means this differential equation is not an exact differential equation. So now what? So when a differential equation is not exact, we will one by one check these three conditions. First, if my minus nx by n, what is it? Is function of y only, or nx minus my by m, is it function of x only, or xm plus yn is not equal to 0 and m and n both are homogeneous function of the same degree. If any one of these condition is satisfied, then we have seen the rules for the solution for that. So what is the integrating factor in that case? We have seen that. So first, for this equation we check nx minus my by m, and it is 2 minus 1 by y, that is 2 by y. So it is function of y only. So as nx minus my by m a function of y only, we have the integrating factor e raised to integral 2 by y dy, that is e raised to 2 log y, and that becomes y square, as e raised to log x, that will be equal to x, e raised to, by that rule we have y square, the integrating factor for this differential equation. So here y square is integrating factor of the differential equation. That means that the differential equation is not exact, but if we multiply the differential equation by y square, it will become exact. Means after multiplying by y square to this differential equation, the equation in the form m dx plus n dy equal to 0, it will satisfy the condition my equal to nx, and with the solution of the type integral m dx plus integral terms in n not containing x with respect to y is equal to c, by that formula we will be able to give the solution for that new differential equation, new form of the differential equation, that is now in exact form. So we multiply the given equation by the integrating factor, that is by y square. So it becomes y cube dx plus 2x y cube minus y cube e raised to y dy equal to 0. Now you can check that after multiplying the given differential equation with y square, we have this differential equation. The original equation was not exact, but after multiplying by the integrating factor, that is by y square, to that differential equation, we have this equation, and if you take this as m equal to y cube, n equal to 2x y cube minus y cube e raised to y, that will satisfy the condition for exactness, means this is an exact differential equation, and so its solution we can give by integral of m, that is y cube here with respect to x, plus integral of the terms in n, that is terms in the coefficient of dy, 2x y cube minus y cube e raised to y, which are free from x. So the second term is free from x, so we have considered that term only, minus y cube e raised to y, we integrate that with respect to y is equal to the arbitrary constant c. And so we have integration of y cube, because in the first term it is integration with respect to x. At that time we treat y as constant, it is y cube x, minus this is y cube e raised to y. So we have to integrate y cube e raised to y using the rule of integration by parts. So using integration by parts rule, we get integration of y cube e raised to y as e raised to y into y cube minus 3y square plus 6y minus 6, and is equal to arbitrary constant. So this is the general solution of the non-exact differential equation that is we have considered first. Now we consider the second non-exact differential equation. It is x square y dx minus x cube plus y cube into dy. You can see that the coefficient of dx is x square y. So if we consider this equation in the form m dx plus n dy equal to 0, this m is a function of degree 3, it is a homogeneous function of degree 3, and this n, it is minus x cube minus y cube, it is a homogeneous function of degree 3. So we have here m and n both homogeneous functions of the same degree 3. Moreover, if we check the condition xm plus yn, whether it is non-zero or not, so x into m plus y into n, that becomes minus y raised to 4, and that is not equal to 0. So 1 upon xm plus yn means 1 upon minus y raised to 4, that will become the integrating factor, means the third rule that we studied earlier. So 1 upon xm plus yn, it is minus 1 upon y raised to 4, that is the integrating factor for this differential equation. So we multiply this equation by minus 1 upon y raised to 4, and it will become exact, and then by the formula of exact differential solution for the exact differential equation, we will give its solution. So the integrating factor is 1 upon xm plus yn minus 1 upon y raised to 4. So we multiply the given differential equation, this is equal to 0, by the integrating factor minus 1 upon y raised to 4, and so it becomes minus x square by y cube dx plus x cube by y raised to 4 plus 1 by y dy equal to 0. Here also you should check the exactness. Okay, so verify that this equation is exact. So this is m is minus x square by y cube, n is x cube by y raised to 4 plus 1 by y. So with this m and with this n, this differential equation is now exact, and so we give its solution by integration of the m with respect to x, treating y as constant, plus integration of the terms in n not containing x with respect to y is equal to the arbitrary constant c. So here y will be treated as constant, and so integration of minus x square is minus x cube by 3, and the integration of the only term free from x is here 1 by y, so its integration is log y. And so the general solution of the second non-exact differential equation, after reducing it to exact differential equation by multiplying the integrating factor, we have minus x cube by 3y cube plus log y equal to c. Now after this we see, let us see the linear differential equation. It is also known as Leibniz linear differential equation and Bernoulli's equation. They are also the first order differential equations. And what about their integrating factors, or what is the technique to get their general solution? Sir.
Now I will introduce the very important equations known as Leibniz linear equation. It is very useful in physical applications. The equation of the form dy by dx plus p the function of x only into y is equal to qx. Here p and q both are function of x only, then the equation in this form is known as the Leibniz equations or linear equations. It is a first order equations. We will try to solve this equation making it exact. First write out this equation in m dx plus n dy form. To do this, let us simplify form. Py minus q dx plus dy is equal to 0 is same as m dx plus n dy. Therefore, m is equal to py minus q and n is equal to 1. Partial derivative of respect to y is equal to p. No, partial derivative of m with respect to y is p, but partial derivative to n with respect to x is 0. That means that my is not equal to nx. The condition for exactness is not satisfied. This equation is not exact. Here my minus nx upon n is a function of x alone, and therefore we can get the integrating factor by the rule number 1 which we have already quoted. The integrating factor will becomes e raised to integral p dx. This is the integrating factor. You multiply this factor by this factor whole equation, then equation becomes e raised to integral p dx into bracket dy by dx plus py is equal to q into e raised to integral p dx. Now the left hand side is directly primitive, that is d dy of y e raised to integral p dx dx of this, and therefore this is directly integrable, and we get the integration as y e raised to integral p dx. Integrating this will get this, and integral of q e raised to integral p dx plus c will become a solution. That means that here we directly get the integrating factor from the given equation, and we will remember whenever the linear equation of this form, the integrating factor is integral e raised to p dx, and the solution is y into integrating factor is equal to q into integrating factor, again integration with respect to x plus c, and immediately we get the solutions. That is a very important equation with very important application in physics. The second is equation which is a generalization of this is known as Bernoulli's equations. Suppose dy by dx into py is equal to q into y raised to n is a equation where p and q again function of x only, and n is belongs to natural number, but it is not equal to 1. If n is equal to 1, automatically is a linear equation and solution is available by linear methods. Therefore, we will take here n is equal to not 1. Even n is 0 also it become a simple differentials, and we will get the immediate integral. Therefore, instead of n is 0 and 1, n can take any value from natural number. We will try to find out solutions. Now, multiply this equation by y raised to minus n throughout, then y raised to minus n dy by dx plus p into y raised to minus n is equal to q, because we have eliminate y raised to n on the left hand side. Now substitute v is equal to 1 y raised to 1 minus n. Therefore, dv by dx is equal to 1 minus n y raised to minus n dy by dx, and that will give you y raised to minus n dy by dx. The value of this will get is equal to y raised to minus n dy by dx equal to 1 upon 1 minus n dv by dx. Now substitute this value in original equations, y raised to n dy by dx plus p y raised to 1 minus n q, and the equation becomes y raised to minus n dy by dx plus py is equal to q. Then value of this substitute 1 upon 1 minus n dv by dx plus py is equal to q. Therefore, dv by dx is equal to 1 minus n pv 1 minus n q. This is a linear equation, and its solution, its integrating factor is equal to, here instead of p n minus 1 p is product of v. Therefore, integrating factor e raised to integral 1 minus n p dx, and hence the solution is v into integrating factor is equal to integral of integrating factor multiplied by 1 minus n q, which is the left hand side, integration dx plus c is arbitrary constant. That way we get the solution of Bernoulli's equations.
Now let us see examples of Leibniz linear equation and Bernoulli's equation. So let us have first example. The first differential equation, it is a differential equation of first order, first degree, and in the form m dx plus n dy equal to 0. But we rewrite this differential equation and we get that it is dy by dx plus 2x upon x square plus 1 into y equal to x by x square plus 1. So which is of the form dy by dx plus a function of x into y plus is equal to a function of x, that is dy by dx plus py is equal to q, where p and q are functions of the independent variable x only. So this is a differential equation of the type Leibniz linear differential equation, and its solution is given by first finding the integrating factor, that is e raised to integration p dx, and then by the formula y into the integrating factor is equal to integration of q into integrating factor dx plus c. So in this case the integrating factor is e raised to integral p dx, that is in p is 2x by x square plus 1. So e raised to integration of 2x by x square plus 1 dx, that is e raised to log x square plus 1, and it is x square plus 1. The integrating factor is x square plus 1. So in the case of Leibniz linear equation, after finding integrating factor, the solution is given by y into integrating factor is equal to q into integrating factor, it's their integration with respect to dx plus c. So it is y into x square plus 1 integration of x by x square plus 1 into x square plus 1 dx plus c, and so the solution is y into x square plus 1 is equal to x square by 2 plus c. Now second is dy by dx plus y equal to xy cube. We can see that it is a Bernoulli equation as it is in the form dy by dx plus py is equal to qy raised to n, this form. So we divide by both the sides by y cube, and we put the coefficient of the term y, that is it is y raised to minus 2 here, the second term